Good day, everyone. My name is Guy. Thank you for joining us for this lightning talk about the Evidence Hub, a place to exchange knowledge and form communities. Let's look at these words one by one. First, this is a dedicated space for computable biomedical knowledge objects. Everything is findable, accessible, interoperable, and reusable, and open source. It is also a fair and equitable place. Here, anyone can publish objects. There's a technical side with payload, with source code, but there's also a non-technical side with discussions or vision history and other metadata. The copyright remains with the owner of the object, but it is released under GPL 2.0. The site is agnostic to the type of biomedical knowledge that's on it. The community decide, like a Wikipedia model. All object handling apps can register themselves using the free API and provide handling such as execution, viewing, and editing of knowledge objects. The site is designed to form communities around areas of interest. These could be technical areas such as analytic workflows or cohort definitions, or these could be around particular diseases, particular devices, therapeutic areas, and so on. The aim is to drive consensus through civil discussion, which is moderated and controlled by the owner of the object. Disagreements can be resolved by branching objects and hopefully not too many heated arguments. Finally, I'm happy to announce that Evidence Hub is now in beta, and participants of the MCBK symposium are welcome to join the beta program and get early access and help form the site, the final version of the site. To do so, feel free to email me or use the QR code on the screen to link in with me. Thank you.
Hello, everyone. I am Dr. Neha Bhasin, representing the University of San Francisco. This presentation, in collaboration with Professor William Bossel, aims to emphasize the importance of computable biopsychosocial knowledge for psychiatric healthcare. Psychiatric disorders impose an enormous burden of disease on all populations of the world. These disorders generally emerge over time due to complex factors, creating opportunities for early intervention to redirect the developmental trajectories and to monitor the efficacy of treatments. Unfortunately, the data necessary to monitor these neurodevelopmental trajectories relevant to psychiatric disorders are typically not collected in routine clinical care. Therefore, we are proposing the creation of a new paradigm for a learning mental health system that is designed around a globally accessible personal psychiatric database that will support research in computational psychiatry and will evolve into clinical decision support systems. Our team comprises a collaboration among the University of San Francisco, Stanford, Harvard, and Boston Children's Hospital. Our methodology integrates three components to create a computable mental health knowledge system. Firstly, a mobile platform to collect the EEG and other relevant data outside of the clinic, as you can see on the top left image, which will be stored in a FHIR-based personal mental health database, and along with the individual's EHR, algorithms will be developed to compute neurodevelopmental risk trajectories from the database. Mandatory consent will be required for running algorithms on this data in a federated manner with a strong focus on maintaining privacy. This slide shows the previous research which has been done, and the research recruited various cohorts to identify biomarkers for neurodevelopmental disorders in children from EEG recordings. These biomarkers successfully predicted outcomes related to autism, as well as detection of childhood anxiety and nocturnal epilepsy. Our nonlinear analysis, tensor factorization, and probabilistic risk assessment algorithms have opened a new window into neural functioning. This is our future plan, which is the initial pilot implementation, which will be housed at Boston Children's Hospital in collaboration with Stanford Biodesign Lab, which will be contributing to the construction of a mobile EEG system and an app for data collection. The USF Center for Healthcare AI will be actively involved in crafting algorithms for the discovery of psychiatric biomarkers. And the hurdles ahead encompass securing sustained funding, establishing effective data governance, and devising pathways for alternative models or federated learning. Thank you.
Good day, everyone. I'm Alan Flynn from the Department of Learning Health Sciences in the Medical School at the University of Michigan. I'm also a faculty member in the School of Information. And today, coming out of our work with the Knowledge Systems Lab and the Knowledge Grid program that we reported out on before, we want to raise a question related to economic incentives and upholding the rights of CBK creators. So the problem for creators is this problem that can be thought of in 3 words, that everything is free. And in fact, that is the name of a song from Gillian Welch, a country singer in the United States, decrying music streaming and what that has meant for musicians who create new music. We've also seen more recently over the last year a lawsuit that authors have filed because their works have been put into the pile of data that has been processed to make tools like ChatGPT and other large language models possible. And so the question has come up whether it should be free to the folks who are consuming those data and creating those large language models to have all of that text and use all of it in that way or not. And of course, this lawsuit and others may begin to iron that out. But the bigger problem is really an economic one. And these are just signs of a major economic issue in our modern networked world. So the question that we're raising is it really possible to make an economically viable CBK ecosystem where creators of CBK artifacts would be able to create, manage, maintain, and sustain their work and get sufficient credit and remuneration for it so that work would be able to continue? And of course, we're raising the question, the answer is uncertain. So the answer today is perhaps that's possible. In the MCBK community, we often speak as if it is possible to create an economically viable CBK sharing community, but it hasn't been achieved yet. And so in our team, we're thinking about some of the things that would need to be done potentially to make that possible. For example, we use the IAA idea here of identification, authentication, and attribution to focus first on giving CBK artifacts unique IDs and digital signatures. Second, to think about access controls and digital keys that would ultimately support payment. And third, that to think about rights of attribution and what it means to use someone else's code to compute something of use in biomedical research or in care, and then give sufficient credit for the capability to do that computation. So these economic incentives will either foster or thwart a powerful CBK ecosystem. The notions that we're bringing forward today have been thought through for CBK, but they're basic notions that came from Walter Isaacson on how to fix the internet in a piece in the Atlantic from 2016. And it involves more than just the IAA, establishing CBK life cycles and understanding the creation patterns, the use patterns, and ultimately the deprecation patterns of CBK. Then these issues of IAA that I've already mentioned, if we can do all of that, we perhaps can enable sufficient micropayments to have a sustainable ecosystem. But the ecosystem would also be threatened by liability issues. And so we're also going to need to treat liability issues from an economic point of view. Thank you for your time and attention. And we look forward to discussing these issues with the community.
We have a major problem with lack of scientific rigor in medical experimentation, care, and research. My colleagues and I posit that we will enable a learning healthcare system if we can automate best evidence-based care for those interventions for which appropriate information exists. Using Dr. Friedman's model, one of the important questions to ask is how credible is the evidence on which we base knowledge and knowledge to performance? And in fact, it's not particularly credible for much of what we do in healthcare. Evidence-based treatments, even when good evidence is available, are delivered only about half of the time. That's due to unwarranted or mindless variation on the part of clinician decision makers that leads to variable clinician action, to very noisy clinical data with both random and systematic noise that reduces the signal-to-noise ratio for important data in clinical outcomes and reduces the validity of the critically appraised external evidence, which ultimately interferes with generation of a learning healthcare system. We have, over the past 3.5 decades, adopted detailed computer protocols that deliver personalized care instructions, beginning with mechanical ventilation, which I'll use as an example here. If ventilator management is left to the judgment of clinicians like me, we can expect the evidence-based care to be delivered only 50% of the time. Contrast that with open loop servo control, in which 95% of multiple hospitals at different institutions and countries deliver appropriate evidence-based care, and closed loop or automated care in which 100% deliver. Remember that these two are called e-actions by us, and they return the best evidence-based personalized care instructions. So they're focused on the needs of the individual patient. What this does is, by acting here, reduces the unwarranted variation, increases signal to noise, decreases the problems with validity, and enables a learning healthcare system. We can address in questions why we would bother to trouble ourselves with the burden of developing e-actions or evidence-based care decision support tools. I extend my thanks to the organizers of the meeting for the opportunity to make this presentation.
Hi, everyone. I am Minerva. I am PhD student at the UNED in Madrid. I want to share with you our experience using REDCap to support the development of a learning healthcare system for patients with multiple sclerosis. First of all, I want to introduce briefly the clinical problem we are facing. As is broadly known, multiple sclerosis is a neurodegenerative demyelinating disease with an autoimmune origin which affects 2.8 million people worldwide. In the right side of the presentation, you can see a representation of the course of the disease. It normally starts with a relapsing, remitting phase characterized by an undefined number of outbreaks and recoveries. After that, it starts a secondarily progressive phase characterized by a permanent loss of functionality. This start could happen 20 years after the diagnosis in a range from 1 year to 51 years. That means a long period of uncertainty, and our system aims to reduce this period. For that, we are following a cohort of 300 patients during 8 months. First of all, we conduct bibliographical research to identify risk factors and associated questionnaires we will use to evaluate these risk factors. We are also capturing data from the electronic health records through REDCap and also from patient-reported outcomes in a semi-automatized way also through REDCap. Once the patient is invited to participate and they think the informed consent, consent, they are assigned a number and a QR code to access the questionnaires. After that, we set a number of reminders sent every 3 months by mail to ask the patients to complete the questionnaires every 3 months. Those are our response rates. Until this moment, we have invited 223 people. 72% of them answered the questionnaires. On the second round, 96 people read this 3 months time, and 66% answered. And the third round has been read by 19 people. 97% answered the questionnaires on this third round. Those are promising results. For us, the conclusions are that REDCap facilitates the collection and management of clinical reported outcomes and patient-reported outcomes with a promising response rate, 73% on the first round. And we are also capturing valuable information regarding quality of life and functionality, which could assess clinical decisions. Thank you for your attention.
Thank you. My title is Which Computable Biomedical Knowledge Objects Will Be Regulated as a Medical Device? And I'd like to acknowledge the contributions of my co-authors and also the British Computer Society. And just before we start, the context is that most users of clinical decision support and also developers as well are concerned about legal liability and regulation of these systems, and of course of medical knowledge objects. So our aim in this project was to understand which computable knowledge objects are most likely to be regulated as a medical device in the UK. And we developed a briefing paper, sent it around to a multidisciplinary group of people, convened a one-day workshop in London, and then we wrote a draft and circulated a discussion paper and got a lot of useful comments back from both participants and also actually from journal referees. And it is now published, pre-published online at Learning Health Systems. There's the QR code if you want to check it out. So we start with some key definitions, and note that this is for the UK. That doesn't now include Northern Ireland because they're still subject to EU law, but we believe that most of these definitions are fairly generic, will probably apply in the US and other places because of the work of the International Medical Device Regulators Forum. So as you're familiar with medical devices, I'm sure that they are tools for intended by manufacturers for use by human beings for the purpose of diagnosis, prevention, etc., or investigation. And there are a couple of important embedded definitions there. First of all, software, a set of instructions that processes input data and creates output data. And the medical purpose, which is assigned to a medical device by the manufacturer. So here are our conclusions in algorithmic format. If a knowledge object is supplied with or part of a device, it's automatically regulated as a medical device. If it isn't supplied and doesn't include any software, then it won't be regulated. If it does include software, then it depends on whether the purpose of that knowledge object is medical or not. And there's an explanation there of what that means. If it is medical, it will be regulated. And then another way of looking at this is using Boxweller's knowledge typology, which you'll be familiar with. 4 different levels. We've actually split level 2. But to cut to the chase, our conclusion is that only the 4th type, the executable knowledge objects, will be regulated because they're intended for CDS applications and they become part of a CDS. So that's our conclusions. Thank you very much indeed.